A lone scholar stands on a stone tower, squinting at the night sky. He sees the same stars his ancestors saw, but he is asking new questions, challenging everything he was taught. That same restless curiosity lies in all of us, that deep desire to understand our place in the cosmos. We are about to explore 35 key discoveries in medieval astronomy, a journey that completely reshaped our cosmic perspective. By the end, you will understand how this era built the bridge from ancient myth to modern science. We will uncover why they invented a device that could model the entire heavens, and how a strange mathematical trick secretly paved the way for a solar system with the sun at its center. What part of the night sky makes you feel the most wonder? That scholar on the tower likely held a device of breathtaking ingenuity, a portable engine of the sky known as the astrolabe. Crafted from shining brass, it was a complex sculpture of rotating discs and delicate pointers, a map of the entire heavens condensed into the palm of your hand. This was not a European invention, but a treasure of knowledge that journeyed from the brilliant scholars of the Islamic world into the hands of medieval European monks and stargazers. They called it the mathematical jewel. Its design was pure genius. One disc was a star chart, a fixed snapshot of the night sky, another etched with lines for altitude and azimuth, rotated over it. By aligning a pointer called the alidade with a specific star, you could solve cosmic puzzles that had baffled humanity for centuries. You could tell the time with astonishing accuracy, day or night. You could calculate the sun's path, determine your precise latitude on the Earth, and even forecast the rising and setting of constellations. Suddenly, the cosmos was no longer a realm of pure mystery. It was a clockwork of predictable motion that you could hold, measure, and understand. This single device transformed astronomy from a philosophical pursuit into a practical science, laying the groundwork for every navigator who would later sail into unknown oceans and every thinker who would dare to remap the universe itself. But that brass astrolabe needed something more to unlock its full potential. It needed a key, a set of instructions that could tell you exactly where the planets would be on any given night. That key was forged in the royal courts of Spain under a king known as Alfonso X, a monarch so passionate about the stars that he famously remarked that if God had consulted him during creation, the universe would have been a much simpler affair. His greatest legacy was not a castle or a battle, but a book of numbers, the Alphonsine Tables. This was not a single scroll, but a vast astronomical library compiled by a team of Jewish, Christian, and Muslim scholars working together in Toledo. For the first time, astronomers had a predictive engine. The tables gave them the precise positions of the sun, the moon, and the 5 known planets for every day of the year, calculated decades into the future. They blended the ancient geometry of Ptolemy with new, meticulous observations, creating a celestial timetable of unprecedented accuracy. Imagine being able to look at a chart and know that Mars would be in a specific constellation on a specific Tuesday in the year 1300. This was the power they now held. For over 3 centuries, these tables were the gold standard across Europe, the essential tool for anyone casting a horoscope, planning a religious calendar, or simply trying to understand the clockwork of the heavens. They represented a universe that was at last predictable, yet within their complex calculations lay a quiet tension, a subtle mismatch between the predicted paths of the planets and the reality observed through the eyepiece of a quadrant. This tiny discrepancy was a seed, a quiet question waiting for a future mind to ask. What if the tables are wrong because the model itself is flawed? Yet those planetary tables described a cosmos that was still bound by ancient rules. For over 1,000 years, everyone knew how the universe worked because the great philosopher Aristotle had explained it. He declared that the earthly realm was a place of change and decay, while the heavens above the moon were perfect and eternal, made of a special 5th element called ether. In his view, every single motion required a constant cause. An arrow flew because the air itself pushed it along. The celestial spheres turned because an unmoved mover, a divine intelligence, pushed them for all eternity. This was a universe that needed to be constantly touched, guided, and motivated by an external hand. Then, in the bustling lecture halls of the University of Paris in the 14th century, a philosopher named Jean Baradin asked a very simple, yet revolutionary, question. Why does a thrown stone keep moving after it leaves your hand? If the air is pushing it, Why does a spear, carefully crafted with feathers, cut through that same air instead of being shoved backward? His answer shattered the ancient framework. He proposed that the thrower imparts an internal force to the object, a living energy he called impetus. This impetus is the reason the stone continues its arc. It is not the air but a property within the moving thing itself. Think of a child's top spinning on a smooth table. Your hand gives it a twist and it continues to spin long after you have let go, driven by that initial burst of energy you gave it. Barrington suggested that this impetus would last forever, were it not for resisting forces like air friction or gravity slowing it down. In the perfect frictionless void of space, he reasoned, a body set in motion would just keep moving. This single idea was a quiet earthquake. It meant that the planets and stars, once set spinning by a divine initial push, might not need angels or intelligences to constantly guide their spheres. They could simply coast on the impetus given to them at the beginning of time. This was the first philosophical crack in the ceiling of the crystalline spheres, a suggestion that the mechanics of the heavens might not be so different from the mechanics of a spinning wheel here on Earth, and it opened a door to a universe that could, in theory, run on its own. This quiet philosophical shift needed a mathematical key to unlock the cosmos. While Barrington was rethinking motion in Paris, a Persian astronomer named Nasir al-Din al-Tusi was wrestling with a stubborn celestial problem. The ancient system of Ptolemy required planets to move in perfect circles, yet their observed paths were anything but circular. They would slow down, speed up, and even appear to loop backward in the sky. To explain this, Ptolemy invented a complex device called the equant, a point from which a planet's motion would appear uniform, but this violated the core principle of perfect uniform circular motion around the center, and it deeply troubled astronomers who sought a more elegant truth. Al-Tusi's brilliant solution was a geometric masterpiece known as the Tusi couple. Imagine two circles, one large and one small. The small circle rolls perfectly along the inside rim of the larger, fixed circle. Now picture a single point on the circumference of that smaller rolling circle. As the small circle turns, that single point does not trace another loop. Instead, it oscillates back and forth in a perfect straight line. This was the magic. The Tusi couple generated linear motion from nothing but circular motion. For astronomers, this was a revelation. By applying this two-sphere device to the celestial models, they could now make a planet pulse toward and away from the Earth, or oscillate along a line, using only combinations of uniform circular motions. This eliminated the need for Ptolemy's philosophically problematic equant point, preserving the beauty of circular motion while perfectly replicating the planet's strange dance. It was a mathematical fix of breathtaking elegance, a clever workaround that kept the Earth at the center of the universe for a little while longer, yet within its rolling circles lay a profound secret. By proving that complex, non-circular paths could be built from simple circles, the Tusi couple handed future astronomers the very tool they would need to dismantle the geocentric model entirely. It provided the mathematical language for a new cosmic architecture, one where the sun, not the Earth, would eventually take its place at the center. But how could these new ideas be tested against the real night sky? You needed more than just philosophical insight and elegant geometry. You needed to measure, and for that, medieval astronomers turned to one of the most versatile and enduring tools ever created, the quadrant. This was a beautifully simple instrument, often just a quarter circle of wood or brass marked with a scale from 0 to 90 degrees and fitted with a sighting mechanism. Its principle was pure geometry. By lining up the sights with a star and reading the angle from the plumb line hanging at its center, you could determine its altitude above the horizon with remarkable speed. This simple act of measurement became the foundation of observational astronomy. Its very simplicity led to its proliferation. Soon, specialized forms appeared across the scholarly world. The Harari quadrant was a pocket-sized timekeeper, its curved lines allowing a user to calculate the hour of the day based on the sun's height. For the scholar in a monastery garden or the merchant in a city square, it made the cosmic clock personal and immediate. Yet for the grand questions of planetary motion, something far more substantial was required. In the great observatories of the age, you would find massive mural quadrants, immense brass arcs permanently fixed to a north-south wall, precisely aligned with the meridian. These were not portable tools but permanent fixtures of science, built on a monumental scale to minimize error. An astronomer would wait for a star or planet to cross the meridian, its highest point in the sky, and then carefully note its altitude on this giant, finely divided scale. It was with instruments like these that the subtle discrepancies in the Alphonsine tables were first confirmed, providing the hard, numerical data that would one day force a revolution. The quadrant in all its forms turned the sky into a page of numbers, proving that the universe could not only be contemplated, but also quantified. While the quadrant gave astronomers the numbers, they still needed a map to understand what those numbers meant. That map was drawn not in the stars, but in the pages of a book. In the early 13th century, a brilliant English scholar named Robert Grosseteste sat down to write a concise guide to the cosmos, a text he simply called On the Sphere. This was not a dry academic paper, but a powerful synthesis that would become the standard astronomy textbook for the very first universities taking root in Europe. Grosseteste pulled together the wisdom of the ancient Greeks and the insights of early medieval thinkers, weaving them into a single, coherent vision of the universe. His model was elegantly simple and profoundly influential. He described a spherical Earth, fixed and unmoving at the very center of all creation. Surrounding it was a finite, nested series of transparent spheres, each one carrying a celestial body. The Moon's sphere was closest, then Mercury, Venus, the Sun, and on outward through the planets to the final, star-studded shell that marked the ultimate boundary of reality. This was a universe with a clear shape and a definite edge, a cosmic onion with humanity at its heart. But Grosseteste added a crucial ingredient to this ancient structure, one that reflected his deep fascination with the nature of light. He proposed that light was the very first corporeal form, the fundamental energy that gave matter its dimensionality and set the entire cosmos in motion. In his view, the creation of the universe began with a point of light exploding outward, propagating in every direction until it forged the perfect spherical shell of the stars. Light was not just something you saw, it was the active shaping principle of the cosmos itself, the engine that animated the celestial spheres. Imagine a single pebble dropped into a still pond, the ripples expanding in perfect circles until they reached the shore. For Grosseteste, the universe was that pond and light was that initial generative ripple. This idea that the physical world could be understood through fundamental principles like light and geometry was revolutionary. It inspired a whole generation of scholars at Oxford and Paris to look at the heavens not just as a divine creation, but as a physical system that could be decoded. His book provided the essential mental architecture, the common map that every student of the cosmos would learn from for the next 100 years. It was a stable, Earth-centered universe, but one now crackling with the dynamic energy of light, waiting for the right mind to ask what happened if you moved the center. The stars, mapped so carefully by Grosseteste and his students, were not the fixed tapestry they appeared to be. The cosmos itself was drifting. Medieval astronomers, meticulously comparing their own observations with ancient records left by the Greeks like Hipparchus, detected a subtle but undeniable shift. The entire canopy of the fixed stars was slowly sliding westward, completing one full cycle over a span of nearly 26,000 years. They called this the precession of the equinoxes, a slow wobble in the Earth's rotational axis, like a spinning top beginning to trace a slow, majestic circle before it falls. This was not a motion of the stars, but a motion of our very platform, a revelation that the Earth itself was not a perfectly static plinth. Imagine the celestial pole, the point around which the northern sky appears to turn. Today, we are fortunate to have Polaris, the North Star, marking that spot with reasonable accuracy. But for the ancient Egyptians, the pole star was Thuban in the constellation Draco. And in 12,000 years, it will be the brilliant Vega in Lyra. The medieval astronomers were the first to measure this grand celestial migration with any real precision. This discovery forced a complete revision of the old star catalogs. A star's position was no longer a permanent coordinate, but a temporary address in a slowly evolving sky. For calendar makers and astrologers, this was a profound disruption. The zodiacal constellations, the backdrop for the sun's annual path, were no longer aligned with the seasons as they had been in antiquity. The spring equinox was slowly creeping backward through the signs. This meant that the entire framework of horoscopes, based on the tropical year, was fundamentally out of sync with the actual stellar constellations. The universe was revealing itself to be far more dynamic and ancient than anyone had dared to suppose, its clockwork operating on a timescale that dwarfed human history. This slow, majestic wobble was a silent testament to a cosmos in constant, if imperceptible, motion, challenging the very notion of a fixed and eternal firmament. That slow, celestial wobble made predicting the planets more crucial than ever, yet the mathematics in the Alphonsine tables remained a labyrinth of calculations. For a scholar without a lifetime to spend on geometry, the heavens could feel just out of reach. Then a new kind of instrument emerged, one that traded complex arithmetic for elegant mechanics. It was called the equatorium, a planetary calculator made of brass and parchment. Think of it not as a tool for observing the stars, but as a miniature working model of the entire Ptolemaic universe, designed to be manipulated by hand. At its heart were scaled-down versions of the epicycles and deferents that governed each planet's path. A deferent was the main, large circle around the Earth, while the epicycle was a smaller circle whose center traveled along the deferent's rim. The planet itself rode on the edge of this smaller epicycle. This double motion created the observed loops and pauses in a planet's journey. The genius of the equatorium was that it physically built these circles. A master disk, often beautifully engraved, represented the deferent for a specific planet like Mars or Venus. A separate, smaller disk, the epicycle, could be rotated on top of it, its edge marked with a precise scale. The user would first calculate the planet's mean position using the Alphonsine tables, a relatively straightforward task. Then they would take the instrument, set the epicycle disk to the correct position on the deferent, and simply write off the planet's true location in the zodiac from a pointer on the epicycle's edge. It automated the most difficult part of the calculation, transforming hours of tedious geometry into a few moments of mechanical alignment. Suddenly, a student in a university courtyard or a monk in a quiet scriptorium could hold a physical representation of cosmic order, turning dials to see how the abstract circles of Ptolemy translated into the actual position of a wandering star. This was more than a calculator, it was a teacher making the intricate dance of the heavens tangible and accessible. The universe was no longer just numbers in a book, it was a machine you could operate, a profound step towards seeing the cosmos as a system of knowable, physical laws. That mechanical model of the universe, for all its ingenuity, could not account for the sudden, terrifying apparitions that occasionally tore across the orderly night sky. A comet was a rupture in the cosmic fabric, a hairy star that defied all the rules. According to the wisdom of Aristotle, the heavens beyond the moon were a realm of perfect, unchanging order. Comets with their sudden appearance and slow, eerie drift were therefore not celestial at all. They were considered atmospheric phenomena, fiery exhalations from the Earth itself, burning in the upper air like a distant wildfire. They were universally read as omens, divine warnings of plague, war, or the death of a king. Yet a profound shift was underway, driven by the meticulous habits of medieval observers. When a brilliant comet blazed into view in the year 1264, it did not go unrecorded. Astronomers across Europe, including the English Franciscan scholar Roger Bacon, tracked its path night after night. They did not just note its terrifying splendor, they measured its position against the fixed stars, and they discovered something astonishing. As the weeks passed, the comet was clearly moving in a regular path far beyond the moon. Its parallax, the apparent shift in its position when viewed from different locations, was negligible. If it were a mere atmospheric fire, it would have shown a significant parallax, just as a nearby finger seems to jump when you view it with first one eye closed, then the other. The lack of such a shift meant this object was immensely distant, a true celestial traveler. This single, well-documented observation began to unravel 1,000 years of dogma. Here was a body born in the perfect superlunary realm that was changing, moving on a path that crossed the orderly planetary spheres. It was a crack in the crystalline ceiling, tangible proof that the heavens were not the immutable, perfect realm Aristotle had described. The universe was not merely a clockwork of predictable motions. It was a place where new things could happen, where celestial objects could come and go, leaving a trail of data that would one day demand a new physics to explain their journeys. The precession of the equinoxes was a majestic, slow-moving clock, but medieval astronomers began to suspect its gears were not perfectly even. Their own painstaking measurements, when set against the ancient records, suggested the great westward drift of the stars was not constant. Sometimes it seemed to speed up, and at other times it appeared to slow to a crawl. How could a perfect celestial mechanism exhibit such irregularity? The solution they crafted was a theory of breathtaking complexity, an idea known as the trepidation of the equinoxes. This was not a replacement for precession, but a refinement, a subtle wobble superimposed upon the grander wobble. Imagine a vast, slow-moving pendulum swinging through the heavens, causing the entire sphere of fixed stars to rock back and forth over a cycle of several thousand years. This oscillating motion was designed to explain the tiny discrepancies in the observed positions of key reference stars. It was a mathematical patch, an elegant fix to make the old Ptolemaic model better fit the new, more precise data they were collecting. In essence, they were adding a second, smaller gear to the cosmic clockwork to account for perceived stutter in its timekeeping. This theory, championed by scholars like Thabit ibn Qurra in the 9th century, became a standard part of the medieval astronomical toolkit, encoded into the very tables and instruments they used daily. It represents a crucial moment in the history of science, a moment where the data itself began to strain against the limits of the accepted model. Instead of discarding the model, they made it more intricate, weaving new layers of complexity to preserve the Earth-centered cosmos. The universe, it seemed, demanded ever more elaborate explanations to remain at rest. Even as the equatorium's brass dials turned and the Alphonsine tables predicted the planets, a quiet rebellion was stirring in the lecture halls of Paris. Here, a group of 14th century scholars turned their focus to the one celestial body whose motions were supposed to be the most regular of all, the sun. They knew from centuries of observation that the sun did not travel across the sky at a constant pace. Its journey through the zodiac was uneven, moving faster at one time of the year and slower at another. Ptolemy's original model had accounted for this by placing the sun on a simple eccentric circle, a path where the Earth was slightly off-center, but the data, now sharper and more precise, showed that even this was not quite enough to match the sun's actual behavior. The Parisian astronomers, masters of both observation and geometry, proposed a bold fix. They suggested that the sun's eccentric circle itself was not fixed in space. Imagine a hula hoop held slightly off-center around a person. Now imagine that entire hoop is slowly rotating, shifting its off-centeredness over a vast cycle of many years. This moving eccentric was a radical departure from Ptolemy's static model. It meant the sun's path was not a simple, permanent oval, but a subtly evolving one. To further refine its speed, they also embraced Ptolemy's controversial equipoint, a mathematical trick that made the sun's motion appear uniform from a spot that was not the center of its circle. This was not yet a rejection of the ancient master, but it was a clear and deliberate improvement. By tweaking the geometry, they achieved a new level of predictive accuracy for the sun's position. Their work sent a powerful message to the scholarly world. It proved that even the most revered classical authority could be challenged and corrected with better observations and more sophisticated mathematics. The perfect circles of the cosmos were beginning to show their seams, and the astronomers in Paris were not afraid to suggest new stitches. These celestial calculations needed a physical anchor, a fixed point on Earth from which to measure the heavens. That anchor was found not in a scholar's study, but in the quiet, soaring spaces of great cathedrals. In places like the Basilica of San Petronio in Bologna, architects and astronomers collaborated to turn the vast stone floor into a giant scientific instrument. They installed a meridian line, a long strip of brass inlaid directly into the marble, running precisely north-south. High up in the cathedral's roof, a small, carefully drilled hole acted as a camera obscura. At the exact moment of local noon, when the sun crossed the meridian in the sky, a brilliant spot of light would pour through that tiny aperture. It would travel down the vast, darkened interior and land as a perfect, shimmering coin of sunlight upon the brass line. The entire purpose of this immense installation was to catch that single, fleeting moment each day. The precise point where the light spot touched the line marked the date. On the equinoxes, it would fall at a specific central marker. Throughout the year, it would oscillate back and forth along the line, tracing the sun's changing declination with incredible precision. This was the most accurate timekeeper the world had ever known, a cosmic clock that could verify the exact length of the tropical year and check the accumulating errors in the old Julian calendar. Imagine the solemn ritual of it, a priest or an astronomer watching and waiting in the hushed cathedral for that burst of light to confirm that noon had arrived, that the calendar was correct, and that the cosmos was still operating according to a divine, measurable plan. This was more than just telling time. It was a profound act of alignment, connecting the monumental architecture of a church directly to the mechanics of the solar system, proving that the universe could be understood through geometry and light, right here on the solid ground beneath our feet. Yet the sunbeam tracing its path across the cathedral floor was a solitary observation, a single data point in a vast cosmic puzzle. To truly grasp the planetary motions, students needed a complete, tangible model they could hold in their minds. That model arrived in the mid-15th century, not as a new observation, but as a revolutionary textbook. Georg Puhlbach's new theories of the planets did something no previous work had managed. It transformed Ptolemy's abstract geometry of epicycles and deference into a physical, three-dimensional reality. Puhlbach envisioned the cosmos not as a set of mathematical lines on a page, but as a series of solid, transparent spheres nested inside one another like a set of exquisitely crafted glass bowls. Each planet was given its own set of these ethereal shells. A thick outer sphere, the deferent, rotated with a steady, grand motion. Inside it, like a bearing within a race, was a second, thinner sphere that carried the epicycle. And within that, a third, even smaller sphere actually held the planet itself. This was a universe you could almost build with your hands. Puhlbach's genius was in making this complex machinery visual and intuitive. His book was filled with detailed diagrams called volvelles, which were paper discs that could be rotated and layered on top of each other. A student could physically manipulate these paper models, turning the discs to see how the combined motions of the nested spheres produced the planet's looping, retrograde path across the sky. This was a radical departure from the dry, number crunching of the Alphonsine tables. It answered the burning question of what the universe was actually made of. The planets were not just points of light following mathematical rules. They were physical objects embedded in real spinning structures. The Theoria Nova quickly became the standard astronomy textbook across European universities, dominating teaching for over 100 years. It gave an entire generation a common, physical language for the cosmos, a mental architecture of crystalline spheres that felt solid and real. But by making the model so concrete, Puhlbach also made its flaws more obvious. When a future astronomer finally proposed a new center for this beautiful, intricate machine, the shock would be all the greater, because Puhlbach had made everyone believe they could almost touch the turning spheres themselves. Puhlbach's student would become the man who turned these paper models into a precision tool for the entire known world. Johannes Regenontanus took his master's vision of a physical cosmos and translated it into numbers of stunning clarity. He produced the Ephemerides, a book of tables that did something almost magical. It listed the precise daily position of the sun, the moon, and every planet for decades into the future. Think of it as a celestial almanac, a day planner for the heavens. For an astronomer, this meant no more long nights of calculation just to find where Mars would be on a Tuesday. For an astrologer casting a horoscope, it was an instant reference, but its most dramatic application was far from the university library. When Christopher Columbus set sail into the unknown Atlantic, he carried a copy of Regenontanus's Ephemerides. On his fourth voyage, stranded and desperate on the coast of Jamaica, he faced a mutinous crew and hostile locals. His food and trade goods were nearly gone. Then he remembered the tables. He consulted the book and saw that a total lunar eclipse was predicted for the night of February 29, 1504. He called the local chieftains and declared that his Christian God was angry with them and would make the full moon disappear as a sign. When the eclipse began exactly as foretold, the terrified people rushed to provide him with all the supplies he needed. His life was saved by a prediction printed in Nuremberg years before. This was the ultimate power of these new tables. They were not just academic exercises. They were instruments of real-world consequence, proving that by understanding the clockwork of the sky, you could command authority, navigate uncharted oceans, and literally alter your destiny. The cosmos was no longer a mystery to be contemplated, but a system to be used. A star does not twinkle out of mere caprice. That flicker is a tiny message, a clue that the air itself is a lens. Medieval astronomers, pushing the limits of their quadrants and astrolabes, began to decode this phenomenon. They realized that the blanket of air surrounding our world is not an empty void, but a substance that bends the very light traveling through it. This bending, which they called atmospheric refraction, meant that every single observation they made was subtly skewed. A star near the horizon never appears in its true geometric position. The atmosphere acts like a prism, lifting its image slightly higher in the sky, making it seem as if it has risen just a moment before it actually has. For an astronomer timing an eclipse or plotting a planet's course, this was a critical distortion. An error of even a fraction of a degree could throw off their most careful calculations. The great Persian scholar Al-Hazen was one of the first to systematically describe this effect, understanding that it grew stronger as an object sank closer to the horizon, where its light had to slice through a much thicker wedge of air. Think of a straw in a glass of water. The straw appears bent at the surface because light travels slower in water than in air, changing its direction. The atmosphere does the very same thing to starlight, a continuous, invisible bending from the vacuum of space down to the surface of the Earth. This was more than a curiosity, it was a fundamental correction. To achieve real precision, they had to learn to subtract the sky's own illusion from their data. They began to compile tables of refraction, carefully noting how much to adjust the observed altitude of a star based on its height above the horizon. This meticulous work, this accounting for the atmosphere's trick, quietly purified their view of the cosmos. It was a profound admission that to see the heavens clearly, you first had to understand the imperfections of your own window. These brilliant star catalogs were the fine-tuning of the entire cosmic map. While the Alphonsine tables tracked the wandering planets, the accompanying star catalog did something equally vital. It meticulously charted the supposedly fixed background against which all that motion was measured. This was not a simple list, but a detailed census of the night sky, recording the precise celestial longitude and latitude of over 1,000 stars, along with an estimation of their brightness or magnitude. It gave each star a permanent address in the cosmos. For a ship's navigator far from land, this catalog was a lifeline. By identifying key stars and measuring their altitude with an astrolabe, he could determine his latitude and find his way across the trackless sea. For the monk in his monastery, it was a clock and a calendar, the rising and setting of certain constellations marking the passage of the hours and the turning of the seasons with divine regularity. But this catalog's greatest power was its role as a celestial watchdog. By providing a definitive, standardized record of how the sky was supposed to look, it gave astronomers a baseline for detecting the impossible. Any change, any new point of light where none was recorded, would stand out like a single fresh footprint on a pristine beach. The catalog enshrined the ancient belief in an unchanging heaven, yet by its very existence, it created the tool that would one day prove that belief false. It was a paradox written in parchment and ink, a perfect record of perfection that was destined to be broken by a star that refused to follow the rules. A brilliant new star ignited in the constellation Cassiopeia, a point of light so vivid it could be seen even in the daytime sky. For the young Danish nobleman Tycho Brahe, this was not a divine omen to be feared, but a scientific puzzle to be solved with ruthless precision. Night after night, he trained his massive, custom-built quadrants and sextants on the mysterious visitor, measuring its position against the familiar background stars with an accuracy never before achieved. The critical question was its distance. If it were a mere atmospheric phenomenon, as Aristotle taught, it would exhibit a noticeable parallax, appearing to shift its position when viewed from different locations. Yet Tycho's meticulous data showed no such shift. The new star remained fixed in its place among the other stars of Cassiopeia. This single, undeniable fact was a thunderclap that shattered a foundational pillar of ancient cosmology. The heavens were not immutable. Change, the very essence of the corrupt earthly realm, was happening in the perfect celestial sphere itself. A star could simply appear, blazing into existence where nothing had been before. Tycho's published account of this supernova, complete with his exhaustive observations, sent a shockwave through the learned world. It forced every natural philosopher to confront an uncomfortable truth. Aristotle's universe of perfect, unchanging celestial spheres was broken. If a new star could simply manifest in the firmament, then the entire cosmic architecture needed to be rethought from the ground up. This was the crack through which the modern cosmos would eventually flood in, a silent explosion in the distant void that echoed louder than any philosophical argument, proving that the sky itself was alive with transformation. A sudden darkening of the sun was a moment of both terror and opportunity. While many saw an eclipse as a divine portent, a few curious minds saw a chance to measure the heavens. To stare directly at the sun was to risk blindness, but medieval scholars like Roger Bacon discovered a brilliant workaround in the camera obscura. This was not a complex instrument of brass and gears, but a simple, profound application of nature's own laws. The principle was elegant. A small hole pierced in the shutter of a darkened room could project the outside world onto an opposite wall, upside down and in perfect color. By turning this room-sized device toward the sky during an eclipse, they could safely watch the entire event unfold. The brilliant, dangerous disk of the sun became a manageable, pale circle of light dancing on a wall or a sheet of parchment. They could now trace the moon's slow, precise march across the solar face, timing its contact points and measuring the exact diameter of the encroaching shadow. This simple trick of light transformed a frightening celestial spectacle into a quantifiable geometric puzzle. It allowed for a new kind of precision, free from the blinding glare and the watering eyes that had plagued earlier observers. Here was a tool that protected the observer while revealing the mechanics of the cosmos in perfect silent clarity. The camera obscura did more than just safeguard vision. It purified observation itself, creating a detached, almost clinical record of an event that had always been shrouded in fear and superstition. It was a quiet declaration that the universe could be studied, not through direct, dangerous confrontation, but through clever, indirect means, a philosophy that would one day lead to the invention of the telescope and forever change our place among the stars. The relentless motion of the heavens demanded a machine that could keep its pace. Giovanni da Dondi, a 14th century Italian physician and clockmaker, dedicated 16 years of his life to a single, audacious project, a clock that did far more than mark the hours. His astrarium was a masterpiece of brass and intricate gearing, a mechanical universe in a tower of its own. 7 separate faces tracked the sun, the moon, and the 5 known planets, each driven by a complex train of over 100 precisely crafted wheels and pinions. This was not a simple timepiece, it was a physical incarnation of the Ptolemaic system, a working model of the cosmos driven by springs and weights instead of divine intelligences. With a soft whirring of gears, it replicated the very retrograde loops and variable speeds that astronomers observed in the night sky, making the abstract mathematics of epicycles and deference visible to anyone who stood before it. The astrarium made celestial time tangible. You could watch the brass moon cycle through its phases or see Mars begin its backward trek through the zodiac without ever needing to look up at the stars. It was the ultimate expression of the medieval belief in a created, orderly universe, a clockwork cosmos built by a divine clockmaker. By bringing this model down to earth, Dondi democratized the heavens, turning the mysterious dance of the planets into a public spectacle of mechanical predictability. His creation proved that the universe could not only be understood, it could be rebuilt. A quiet revolution was unfolding not in the observatories, but in the university halls of Paris and Oxford. Here, philosophers like John Buridan and his student, Nicole Orsmy, began to dissect Aristotle's cosmos with the sharp tools of logic and reason. They asked questions that cut to the very core of the accepted reality. Why must the Earth be perfectly still at the center of everything? Aristotle argued that if the Earth rotated, an object thrown straight up into the air would not land back in its place because the ground would have moved out from under it. Orsmy tackled this with a brilliant thought experiment. Imagine you are on a smoothly sailing ship, he suggested. If you drop a stone from the top of the mast, it falls straight down to the base of the mast, not landing somewhere behind the ship. The stone shares the ship's forward motion. If the entire Earth were spinning, Orsmy reasoned, the air and everything in it would share that motion, just like the air on the ship. A stone thrown upward would simply be carried along, landing exactly where it was thrown from. This single argument dismantled one of the strongest proofs for a stationary Earth. It was a conceptual leap of staggering proportions, suggesting that we might not feel our own planet's motion because we are moving right along with it. They even challenged the uniqueness of creation itself. Why could there not be other worlds, other Earths, each with their own center? Aristotle declared it impossible. But these thinkers saw no logical barrier in the mind of an all-powerful creator. Their critiques did not immediately dethrone the Earth, but they did something far more important. They made the idea of a moving planet philosophically respectable, a topic that could be debated by serious scholars without accusations of heresy. They created an intellectual environment where the old certainties were no longer safe, where the crystalline spheres could be questioned, and where a new cosmology could begin to take root in the fertile soil of doubt. This intellectual earthquake, cracking the foundations of Aristotle's perfect heavens, was fueled by a quiet project of staggering ambition. While scholars in Paris debated the motion of the Earth, teams of translators in sun-drenched cities like Toledo and Sicily were undertaking a rescue mission for knowledge itself. They worked in bustling scriptoriums, often in teams of 3, a scene of intense collaboration. A Jewish or Muslim scholar would read aloud from an original text in Arabic or Greek, translating it phrase by phrase into the common vernacular of Spanish. Then a Christian cleric, fluent in that local tongue, would render it into formal Latin, the language of European universities. This was the Great Translation Movement, a deliberate, organized effort to reclaim the lost wisdom of the ancients and the groundbreaking work of Islamic astronomers. They recovered Ptolemy's Almagest in its entirety, the very blueprint of the geocentric universe. They translated Aristotle's entire body of work on physics and the cosmos, which would both inspire and constrain European thought for centuries. And they brought over the meticulous observations of scholars like al-Battani, whose data was far more precise than anything surviving from Rome. Think of a great library abandoned and crumbling, its books scattered and written in forgotten languages. The translators were the preservers, the restorers, carefully gathering every page, deciphering every script and copying it all into a new, universal language. This was not merely copying, it was a rebirth. European astronomy, which had been languishing with incomplete and often inaccurate texts, was suddenly refounded on a foundation richer, deeper, and more accurate than anyone had dreamed possible. It was like giving a cartographer who only knew his own valley a complete map of the entire world. The translation movement provided the raw material, the intellectual fuel for every discovery that followed. It sparked the controversies that energized the universities and gave the thinkers the tools they needed to first repair, and then ultimately dismantle, the ancient cosmos. This recovery of lost knowledge did not just inform Europe, it set its mind on fire. Yet that mechanical clockwork universe, for all its intricate gears, was built upon a flawed foundation. Far to the east, in the rolling hills of 13th century Persia, a group of brilliant minds had already begun to assemble a better one. They gathered at the Maragha Observatory, an imperial institution funded by the Ilkhanate ruler Hulagu Khan, and their mission was nothing less than a complete overhaul of the cosmos. Here, scholars like Nasir al-Din al-Tusi and Muhammad al-Din al-Urdi were not content to simply accept Ptolemy's word as final. They saw the philosophical problem at the heart of his system, the equant point, as an unacceptable fudge. Ptolemy had planets moving on circles, but to account for their changing speed, he made them sweep out equal angles and equal times from a point that was not the center of their circle. This violated the sacred principle of uniform circular motion around a single central point. Al-Urdi devised a stunningly elegant geometric solution, now known as the Urdi lemma. He showed mathematically how you could replace the off-center equant with an additional, smaller epicycle, one that would perfectly mimic the planet's variable speed while keeping all motions truly uniform around their own centers. It was a fix of pure geometric genius. Al-Tusi then incorporated this and his own Tusi couple into a comprehensive new planetary model, a system that banished the equant entirely. This was not a minor tweak, it was a full-scale architectural revision of the heavens, creating a universe that ran on nothing but combinations of perfect, uniform circular motions. The work produced at Maragha was compiled into a revolutionary text, the Zij-i-Ilkhani, a set of astronomical tables and models that represented the most advanced and self-consistent cosmology on Earth. For generations, this was seen as a purely Islamic golden age, a local revolution, but knowledge has a way of traveling. Centuries later, when Nicolaus Copernicus sat down to devise his own sun-centered system, he faced the exact same problem: how to explain the planet's uneven speeds without an equant. The solution he proposed, a geometric device mathematically identical to the Tusi couple and the Urdi lemma, appeared in his work as if from nowhere. Historians have long debated how this could be, finding no direct evidence of a translated manuscript, yet the coincidence is simply too perfect. It seems the ghost of Maragha, the spirit of its elegant, equant-free models, had seeped into the intellectual groundwater of Europe, providing the crucial mathematical tools that made a sun-centered universe not just a philosophical dream, but a geometric reality. That sphere of fire was a beautiful and logical idea, a layer of pure elemental flame just below the moon, a convenient place to tuck away all the messy, changeable phenomena that did not belong in the perfect heavens above. Comets, with their sudden, smoky tails and unpredictable paths, were the prime residents of this fiery suburb. They were not true celestial bodies, just local atmospheric fires, and this belief was a cornerstone of Aristotelian physics for over 1,000 years. Yet the medieval observers, with their quadrants and their meridian lines, began to gather evidence that this convenient theory was simply wrong. They tracked the paths of these hairy stars with a new level of precision, plotting their movement against the fixed constellations night after night. The critical clue was parallax. If a comet was truly a local fire burning in the upper atmosphere, then two observers in different cities should see it in slightly different positions against the starry backdrop, just as your finger appears to jump when you view it with first one eye closed, then the other. But time and again, the observations showed no such shift. The comet held its position among the stars with a fixed celestial rigidity. This meant it was not a nearby atmospheric flicker, but an object immensely distant, far beyond the moon. It was traveling through the realm of the planets, a place that was supposed to be eternally unchanging. This single, repeated observation tore a hole in the sphere of fire and shattered the boundary between the corrupt, changing earth and the perfect, immutable heavens. A comet was not a terrestrial exhalation, it was a celestial traveler. Its very existence proved that change did happen beyond the moon, forcing a complete rethinking of the cosmic architecture. The tidy layered universe was falling apart, revealing a cosmos far more dynamic and mysterious than anyone had dared to imagine. The most important date in the Christian world depended entirely on the moon. Easter was defined as the first Sunday after the first full moon following the vernal equinox, a rule that tied the holiest day of the year to 3 separate celestial cycles. This was not a simple calculation. It demanded a deep, practical understanding of the sun's yearly journey and the moon's monthly phases, forcing monks and scholars to become expert astronomers out of sheer necessity. They had to predict the exact moment spring began and forecast the lunar phases years in advance, all while relying on the increasingly faulty Julian calendar. This calendar, established by Julius Caesar, had a tiny but cumulative error. Its year was just 11 minutes longer than the true solar year. Over centuries, those minutes added up to entire days. By the late Middle Ages, the calendar had drifted so far that the vernal equinox was falling on March 11th instead of March 21st, throwing the entire computation of Easter into chaos. The very fabric of religious time was fraying because of an ancient miscalculation. This pressing need for accuracy sparked the first serious proposals for calendar reform. Figures like the English friar Roger Bacon wrote passionate treatises to the Pope pleading for a correction. They argued that to honor God properly, the Church needed a calendar that reflected the true heavens, not the drifting dates of an old Roman system. The immense intellectual effort poured into the Easter computers transformed the monastery scriptorium into a center for astronomical refinement, proving that the desire to mark a single sacred Sunday could drive centuries of precise celestial observation and ultimately force humanity to recalibrate its relationship with time itself. Even the moon's dark face holds a secret light. When the moon is a slender crescent, you can often see the outline of its full disk, softly illuminated by a faint, ghostly glow. For centuries, this phenomenon was a source of mystery, called the moon's ashen light or earthshine. Some ancient thinkers speculated it was a faint light emanating from the moon itself, while others imagined it was the glow of distant, unseen stars filtering through. But in the medieval period, a few sharp-minded scholars proposed the correct and rather beautiful explanation. That gentle light was not the moon's at all, but our own. They reasoned that when the sun's light strikes the earth, our planet does not simply absorb it. Like a great cloudy mirror in the void, the earth reflects a portion of that brilliant sunlight back out into space. And when that reflected light falls upon the dark, unlit portion of the crescent moon, it casts this subtle secondary illumination. Think of standing in a dark garden at night, holding a pale stone in your hands. If someone shines a bright flashlight onto a white wall behind you, you will see your own hands and the stone glow in the reflected light. The medieval astronomers realized the Earth and Moon were doing the very same celestial dance. This was a small insight with profound implications. It meant the Earth was not a dark, non-luminous body distinct from the heavenly lights, but an active participant in the cosmic play of light. Our world seen from the moon would be a brilliant object in the sky, many times larger and brighter than any star, a beacon casting its own ashen light upon the lunar landscape. This understanding of Earthshine quietly dismantled another pillar of the old hierarchy, proving that the nature of light and reflection was a universal principle, binding the Earth and the heavens together as one interactive system. Our world was no longer the only possible world. As the cracks in Aristotle's perfect cosmos widened, philosophers dared to ask a question that was both thrilling and terrifying. Could God have created other Earths? William of Ockham, a Franciscan friar known for his razor-sharp logic, argued that the sheer omnipotence of God meant such a thing was entirely possible. If God's power was infinite, what logical barrier could possibly prevent him from creating another world, or even 1,000 worlds, each with its own sun and moon and living creatures? This was not a claim that other worlds existed, but a profound defense of divine freedom. To say God could not create them was to limit the limitless. Nicole Orsmy took the idea even further, dissecting Aristotle's physical objections one by one. The ancient philosopher claimed that if there were another Earth, its elemental matter would naturally rush to our own cosmic center, merging into a single globe. Orsmy countered with a brilliant thought experiment. He suggested that each world would have its own center of gravity, its own natural place. The Earth of another world would fall toward its own center, just as our Earth falls toward ours. Imagine two great magnets, each powerful enough to attract iron filings, but placed far apart in a vast room. The filings near one magnet would fly to it, completely indifferent to the pull of the other. In Orsmy's mind, the cosmos could be filled with such independent centers, each a self-contained universe. This was a radical decentralization of reality. Humanity was no longer the inevitable focus of all creation, but merely the inhabitants of one world among many potential worlds. These debates were not mere academic games. They were a fundamental expansion of the medieval imagination, pushing against the walls of a cozy, anthropocentric universe and gazing out into a void filled with infinite divine possibility. The very stars in the sky suddenly became not just lights, but potential suns for other races, other lives, other stories unfolding in the profound silence of God's endless creation. That looping backward dance of a planet was the ultimate celestial puzzle. You would watch Mars, a steady red point of light, marching eastward through the constellations for months. Then, without warning, it would slow to a halt, reverse its course, and trace a glowing loop in the sky for a few weeks before stopping again and resuming its original journey. This retrograde motion was a direct challenge to any simple model of the heavens. If all the planets just moved in perfect circles around the Earth, this strange backtracking made no sense at all. The medieval astronomers, armed with the geometric toolkit of Ptolemy, had their answer, and it was a thing of elegant mechanical beauty. They called it the epicycle and deferent system. Imagine a planet like Mars is not simply on a circular track around the Earth. Instead, it rides on a smaller, local circle called an epicycle. The center of this little epicycle circle is, in turn, carried along a much larger circle around the Earth, known as the deferent. The planet is like a horse on a merry-go-round, while the entire merry-go-round itself is moving along a giant, circular racetrack. Now picture this double motion from our vantage point here on Earth. For most of the time, the planet's motion on its little epicycle is in the same direction as the big deference motion around us. The combined effect is a steady forward march. But when the planet reaches the part of its epicycle that is closest to us, its local backward swing on the little circle can actually overpower the forward motion of the big circle. From our perspective, the planet appears to slow, stop, and briefly swim backward against the starry background before the forward motion of the deferent carries it on its way again. This was the genius of the model. It did not just explain the loop, it predicted it. Using the Alphonsine tables and an equatorium, an astronomer could calculate exactly when Mars would begin its retrograde dance and precisely which stars would form the backdrop for its loop. This was a key triumph, turning a bewildering celestial anomaly into a predictable geometric certainty. The universe, with all its apparent chaos, was revealed to be a machine of sublime order, its gears hidden in the perfect, invisible mathematics of circles moving upon circles. A physician's most critical tool was not a scalpel or a potion, but a calendar of the heavens. In the bustling medical schools of medieval Europe, a doctor's diagnosis was incomplete without consulting the current positions of the planets. This was the world of astrological medicine, a practice that wove the cosmic and the clinical into a single, inseparable art. The fundamental belief was that the human body was a microcosm of the universe, a tiny reflection of the grand celestial macrocosm. Each organ and bodily function was governed by a specific planet or zodiac sign. The brain was ruled by the moon, the heart by the sun, and the liver by Jupiter. A physician would first consult an astronomical almanac, derived from tables like the Alphonsine, to determine the precise alignment overhead before he would ever dare to treat a patient. The most striking symbol of this belief was the zodiac man, a detailed illustration found in countless medical texts. This diagram showed a human figure with lines connecting each body part to a sign of the zodiac. Aries governed the head, Taurus the neck, and so on, down to Pisces ruling the feet. This chart was his practical guide. If a patient had a headache, the doctor would check the chart and see that the head was under the dominion of Aries. He would then wait for the moon to be passing through Aries before performing any procedure, especially the most common one of all, bloodletting. The logic was clear: the body's vital forces ebbed and flowed with the cosmic tides. To operate on a limb when its ruling sign was ascendant was to invite disaster, as the body part was considered overly charged with celestial energy. The timing was everything, a surgical appointment set by the stars themselves. These celestial prescriptions dictated the entire rhythm of medical care, from the mixing of herbal remedies to the setting of bones, proving that the universe's influence reached not just the soul, but the very flesh and blood of humanity. Even the sun itself was not immune to imperfection. Against the clear doctrine of a flawless celestial body, medieval skywatchers occasionally documented something they could not explain: dark blemishes marring the face of our star. These were not systematic studies, but rare and startling observations, likely made when a thick haze at sunrise or sunset acted as a natural filter, dimming the sun's blinding glare to a bearable intensity. In that softened light, they saw spots, transient shadows drifting slowly across the solar disk. Imagine the cognitive dissonance of that moment, staring at a living contradiction. Aristotle had decreed the sun a perfect, unchanging orb of pure fire, a hallmark of the incorruptible heavens. Yet here was visual proof of something else entirely: a sun that was marked, dynamic, and apparently flawed. These tentative glimpses were often dismissed as atmospheric phenomena or optical illusions, but the most meticulous observers would have noted a crucial detail: the spots moved. They appeared on one limb of the sun, traversed its face over several days, and vanished over the opposite edge. This was not a cloud or a passing bird. It was a feature of the sun itself, a slow rotation revealed by its own imperfections. Each recorded spot was a silent challenge to the ancient ideal, another crack in the facade of a perfect cosmos. It suggested that the sun, the very heart of the planetary system, was a physical object with a changing surface, a place where things happened. These fragmented records, scattered in monastic annals, were the hesitant first steps toward a revolutionary truth: that our sun is not a symbol of eternal perfection, but a dynamic spinning star, and its temporary blemishes would one day reveal the furious activity churning at its core. A teacher's simple model of the cosmos could now be engineered into a masterwork of observational precision. The armillary sphere evolved from a classroom demonstration into the centerpiece of any serious observatory, a skeletal globe of polished brass rings that framed the heavens themselves. At its heart was a central earth ball, but the true genius lay in the multiple nested circles surrounding it, each one representing a fundamental celestial path. The equator ring stood fixed, while the ecliptic ring, tilted at an angle, traced the sun's yearly journey through the zodiac. Other rings marked the Arctic and Antarctic circles, and a movable sighting bar called the alidade could be pivoted to line up with any star. This was no longer just a diagram, it was a direct measuring engine. By rotating the various rings to match the local latitude and time, an astronomer could sight a planet through the alidade and read its position directly off the graduated scales, determining its celestial longitude and latitude with remarkable speed. The entire instrument became a physical embodiment of the coordinate grid of the sky. In the great observatory of Tycho Brahe, massive armillary spheres, engineered with breathtaking precision, were the primary tools for mapping the planets. They turned the abstract concept of the celestial sphere into a tangible, mechanical reality you could reach out and adjust with your own hands. This refinement marked a pivotal shift, transforming a philosophical prop into a data-collecting machine that would provide the accurate positional records needed to finally challenge the ancient cosmic order. A spherical Earth was not a question for the medieval scholar, it was a geometric fact. Long before explorers sailed off the edge of the world, astronomers were already measuring its vast girth with nothing more than shadows, stars, and pure reason. They were following a path blazed centuries earlier by the Greek librarian Eratosthenes, who famously calculated the planet's circumference by comparing the sun's angle in two different cities at the same moment. Medieval thinkers, armed with new tools and a passion for precision, revisited this grand experiment. A scholar might travel from a monastery in northern France to one in southern Italy, carefully measuring the difference in the sun's altitude at noon on the summer solstice using a massive quadrant or a simple, finely crafted gnomon. They knew that this difference in angle, when compared to the known distance between the two locations, was a direct fraction of the Earth's total circle. If the sun's rays fell 7 degrees apart over a journey of 500 miles, then those 500 miles represented 7/360ths of the entire globe. The math was elegant, a simple rule of 3. The results they achieved were often startlingly close to the modern value of about 24,900 miles. This was not guesswork, it was rigorous observational science. These calculations demonstrated a profound confidence in a spherical world, a reality so ingrained that they used it to navigate, to map, and to understand their place in the cosmos. They stood on the ground and, by measuring a sliver of shadow, comprehended the scale of the entire planet, proving that the greatest mysteries could be solved with patience, geometry, and a deep trust in the uniformity of nature's laws. A darkening moon was more than a spectacle, it was a celestial receipt. Monks in chilly European scriptoria and scholars in candlelit Islamic observatories would carefully unroll their scrolls and prepare their ink, knowing they were about to witness a direct test of their astronomical tables. They timed the eclipse with water clocks and sandglasses, noting the exact moment the Earth's shadow first kissed the lunar limb, the instant of totality when the moon glowed a dull copper, and the precise second the last sliver of shadow slipped away. This was not a solitary act, but a coordinated, centuries-long project. From Baghdad to Oxford, these meticulous records accumulated, forming a vast, long-term dataset of celestial mechanics. Each eclipse was a checkmark in the cosmic ledger, verifying the predictions of the Alphonsine tables, or, just as importantly, revealing their tiny, accumulating errors. When a forecast was off by even a few minutes, it forced a refinement of the lunar models, a subtle tweak to the epicycles that govern its speed. This patient, collaborative work transformed eclipses from omens into tools. By working backwards through this precise historical record, a scholar could pinpoint the exact date of a famous battle described in an ancient chronicle as happening under a darkened moon, settling historical debates with the impersonal authority of orbital mechanics. The universe was keeping a time log, and humanity was finally learning how to read it, one shadow disk at a time. That red point of light, Mars, does not move at a steady pace. Its speed is a story of constant change, a narrative written in acceleration and deceleration that defied simple arithmetic. How could medieval astronomers capture this fluid motion with the rigid tools of geometry? At Oxford University in the 14th century, a group of brilliant thinkers known as the Oxford calculators devised a powerful new method, a conceptual breakthrough they called the latitude of forms. This was not about north-south positioning on a map, but about visualizing the intensity or degree of any changing quality, especially motion. They imagined drawing a picture of speed itself. Picture a simple rectangle. Its height represents a constant speed, say a steady walk. The area of that rectangle, its height multiplied by its width, gives you the total distance traveled over that time. This was intuitive, but what about a planet that starts slow, speeds up, and then slows down again? The calculators learned to graph this changing speed. They would draw a curved line where the height of the curve at any point showed the planet's instantaneous speed. The area under that curve, even if it was a complex shape, still represented the total distance covered. This was a revolution in thought. They were translating motion into geometry, turning time and change into a shape whose properties could be measured and calculated. It was a direct precursor to the graphs we use in physics today, a way to see the invisible. By representing a planet's variable velocity as a geometric figure, they could apply the precise logic of mathematics to the messy reality of non-uniform motion in the heavens. This graphical method gave them a new language to describe the cosmos, a language of shapes and areas that could handle acceleration long before the calculus was formally invented. It was a quiet, abstract triumph, one that moved astronomy from simply tracking positions to analyzing the very nature of change, providing the mathematical sophistication needed to one day ask if the planets themselves were governed by a universal physics of motion. That abstract language of motion needed a permanent home, a fortress for the stars. The Great Leap Forward was not just a new instrument, but a new institution, the dedicated university observatory. For centuries, astronomy had been a portable science, practiced from monastery gardens or temporary platforms. But in the 15th century, universities in Vienna and Krakow began constructing towers specifically designed for watching the heavens, institutionalizing the study of the stars. These were not just buildings, they were engines of discovery. Their sturdy, purpose-built walls could support massive, permanently mounted instruments that a lone scholar could never hope to own or operate. Imagine a mural quadrant, an immense brass arc precisely fixed to a north-facing wall, its scale so large that the smallest divisions could be read with stunning accuracy. Or a giant armillary sphere, bolted securely to a stone floor, its rings perfectly aligned with the celestial poles. This permanence changed everything. An observation made by a professor one night could be verified by his students the next, using the exact same instrument, eliminating the errors that came from portable tools being set up afresh each evening. These observatories became hubs of collaborative work, places where a community of scholars could gather to debate a measurement, share a new calculation, or simply wait together for an eclipse to begin. Knowledge was no longer a solitary pursuit locked in a single mind, but a collective enterprise built brick by brick and observation by observation. The founding of these centers marked astronomy's final transition from a philosophical pastime into a modern, data-driven science, creating a legacy of precision that would soon provide the evidence to topple the very universe they were built to measure. The cathedral of medieval thought was built to house a stationary Earth, yet whispers echoed from its very foundations, suggesting a different architect. Long before Copernicus rearranged the cosmos, a handful of daring minds were already questioning the central stage granted to our world. In the 15th century, the German cardinal and philosopher Nicholas of Cusa gazed at the heavens and proposed a staggering idea. He argued that the universe has no single center and no outer boundary. For Cusa, the Earth could not be the motionless pivot of all things because God's creation was infinite, and every point in that infinity could claim its own centrality. He even suggested the Earth was already in motion, a noble star like any other, shining with its own reflected light. This was not a detailed mathematical model, but a profound philosophical leap that stripped the Earth of its unique, privileged status. Across the Mediterranean, Islamic scholars had been nurturing similar seeds for centuries. In the 9th century, the Persian astronomer Abu Mashar speculated that the circular motions of the heavens might be better explained if the Earth itself rotated. Another, Al-Sijzi, designed astrolabes based on the premise that the daily motion of the stars was an illusion created by our own spinning planet. These were not yet full heliocentric systems, but they were powerful thought experiments that chipped away at the geocentric consensus. They asked the forbidden question, what if we are the ones moving? These scattered insights, from the speculative theology of Cusa to the geometric daring of the Islamic world, reveal a cosmos already stirring with revolutionary potential. The Great Shift was not a sudden thunderclap from a single genius, but the slow, inevitable flowering of seeds that had been planted and nurtured in the rich soil of medieval curiosity, patiently waiting for the right mind to give them mathematical form. This long and winding journey through the stars reveals a truth we often overlook. The medieval era was no dark age of superstition, but a vibrant, thousand-year workshop of the mind. From the brass astrolabe to the paper volvel, from the translation halls of Toledo to the observatory towers of Vienna, a global community of scholars was tirelessly building the essential bridge. They took the raw marble of ancient Greek and Islamic knowledge and carved it into a new vision of the cosmos, refining its mathematics, testing its predictions, and daring to question its very foundations. They gave us the tools, the data, and the philosophical courage that made the Copernican revolution not just possible, but inevitable. Every time you look up at the night sky and understand that you are standing on a planet orbiting a star, you are seeing the universe through a lens they helped to polish. We have walked through 35 key discoveries, but this is only the beginning of the story. Which of these medieval breakthroughs captured your imagination the most? Was it the mechanical genius of the astrarium, the quiet rebellion of Buridan's impetus, or the mathematical elegance of the Tusi couple? Let me know your thoughts in the comments below, and if you enjoyed this journey into history's greatest mysteries, be sure to subscribe for our next exploration into the